Okay, hello everyone. It is Friday morning, and that means that it is once again time to do the weekly studio review. So it's a big week. We introduced you to some important concepts, if statements, and loops. And this was also kind of a challenging studio, although I have to say I was very impressed to see how far students got on this studio. This is the first one that students tend to run out of time to finish, so if that happened to you, don't worry about it. That's actually not unusual. We try to keep the studio problems, short enough to finish within class, and some people did, but remember the goal is to show up and participate, think about these problems for the time that you're in class. So let's go ahead and get started with the first part of the studio, which is simulating some gambling. I think it's important to understand the setup for this problem before you start to write some code. Our job is to go to a casino and gamble some money. And the game is pretty simple. We're just gonna, excuse me, play a game, and every time we win $1, and every time we lose $1. So if the amount of money that we ever win hits some predetermined amount that we're happy with, then we're going to stop playing. We've hit our goal for the day. We've won the amount that we want to win, and we're going to go home. If we happen to hit the opposite situation where we lose all of our money, hit $0, then we're going to go home. So what we want to know is this a reasonable job that we can expect to do well at? Can we make a living doing this? And how do the variables affect the answer to that question? The games that I play, the chances that I have of winning, things like that. So let's go ahead and get started. This studio, we actually don't give you any code to begin, so we want you to make the file yourself. Get used to starting from scratch. So I'm going to go ahead and do that, and oops, wrong way there. Here we go. Create a new class. This one I'll call Gambler Simulation. I'm going to check this box here. This inserts what's called the main method. You probably remember me saying that this is what indicates to the computer that we're going to start here. This is the beginning point of the program. And so Eclipse has given us our main method with an empty spot for us to begin. Okay, the instructions next ask us to have our program accept inputs. In order to do this, we use scanner. So I'm not going to spend a whole lot of time talking about that. I'm just going to go ahead and insert the scanner code that we've been using. And if you had to go back to a prior assignment or a prior studio and grab this code, that's totally fine. That's expected and not a problem at all. I'm going to go ahead and import the scanner tool that needs to happen by hovering over and clicking import. And then we can go ahead and start asking for these variables. So I want a start amount, which is an amount of money that we start with. I expect that since we're only winning and losing $1 each time, we could probably keep this as an integer, would be my guess. So I'm going to start with that, and if we need to change it later, we can. Start amount. In.nextInt I will use to grab that. I need to probably put a message here. Okay. Then we will enter similar instructions for using the other variables that are asked for. Win chance, so this is about the game itself. What are the odds that I'm going to win? If I expect this to be a value between 0 and 1. That's typically how we measure probability, so this is going to be a double. Win limit then would be the amount of money that we want to consider going home. So if we do well, if we hit the win limit, then this means we've had a successful day. We're going to stop. All right, let's go ahead and you can see I've copied this code 3 times, and I'm going to tweak it to accept the remaining 2 variables. This will be a double called win chance. And then this will be called what did they say? The win limit. Great. Okay. All right, we now have the three variables that we need to begin our simulation, and so we can actually start by simulating a single day. Remember, a single day consists of playing the game over and over and over again until one of two things happens. We're either going to hit our win limit. We're going to win a lot and hit the amount that we say, all right, we've won a lot, we're going to stop and go home, or we're going to run out of money. We're going to lose all of our cash, we're going to hit zero. We need to keep playing the game until one of those two things happens. So, I think this is a clear indication that we need to use a while loop here. You may consider using a for loop instead, and I think that's also an acceptable way of approaching this problem. I think a while loop does work a little bit better in this situation. Maybe that'll make a bit more sense after we complete the problem and circle back and talk about why I prefer a while loop in this situation. But let's start by trying to code some things. We know that one of the two situations we're trying to account for is losing all of our money. So if we, if we consider that the start amount is the amount that we're starting with, right? So while the start amount is greater than 0, I want to keep playing the game because I haven't run out of money, so I'm going to keep playing this game until I do run out of money. That's one of the conditions that we are interested in trying to track. Okay, so now we just need to simulate playing the game and consider the simple case first. When I explain this to people in class, forget about the win chance for a second. Just imagine the game we're playing is flipping a coin, Heads, I win $1, tails, I lose $1, something like that. So the win chance in that situation would be 50-50, right? So we need a way of simulating that. We need a way of figuring out how we can randomly simulate events, and we've introduced you to the idea of math.random. Now remember that math.random gives us a value between 0 and 1. So if we want to simulate coin flips, then we would expect, half of the values would be greater than 0.5, and half of them would be greater than, or less than 0.5. So I could write something that says, if math.random is less than 0.5, that means that I flipped a heads and I win $1, right? Otherwise, I have flips tails and I lose $1. We need to be careful though, because we're not coin flipping here. We're actually playing the game at the casino, whatever game it is that we've chosen. We want to be able to change the chance of winning so that we can see how that affects the simulation, right? 50-50 odds, if you know anything about going to the casino, that's pretty good odds on a casino game. You're not likely going to see many games giving you such good odds. So we want to be able to change this, and we want to be able to reflect the win chance on our earnings. So now we're saying, all right, if we have a 70% chance of winning, that means that if the value that is chosen is less than 0.7, right, that would be 70%, then we win $1. I expect that to happen 70% of the time if win chance is 0.7. Otherwise, we've lost $1. If the win chance is really low, like 10%, like a very stacked game against us, then you would see that, okay, I'm going to start losing money very quickly. All right. This should have the effect of simulating the game, right? Let's try it out. Let's see. I'll just add one final line down here to print out start amount at the end, and let's go ahead and see if we can simulate. I'm going to type in 100 with a win probability of 0.2 and a win limit of $1,000. And you can see that it did print out 0, right? So I did eventually get down here. Let's see if I can maybe add some more information. I'll put in a message here to say when I win, and a message here to say when I lose, so that I can more clearly see what's happening. I'll try to use the same values as before too. Alright, so you can see lose, 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 lose with a few wins sprinkled in, right? Very much losing though most of the time until eventually I lose all of the money and I go home broke. Let's try another example where the game is maybe a bit more generous. So now I'm going to say 100 with a win probability of like 0.9 and a win limit of, you know, $500. And let's let this one run. And you can see that, oh, okay, it's still going. You can see the results are being printed down here at the bottom. I see a lot more wins than losses going by. But for some reason, it still hasn't actually stopped. And so maybe we could try and get some more information here, figure out what's going on. You know, I would like to see how much money we've got. So let's see. Let's add the start amount onto the message when we win and lose. And then see if we can use that to help us figure out what's going on here. I'm going to try a very generous game. Oh, okay. So you can see that the winning is working, right? But it's just never stopping. I keep winning, and I'm basically living at the casino because I'm enjoying the great odds that I'm getting on this game, which is probably what would happen if casinos ever did offer odds like that on a game. But the bigger issue that we have here is that we never actually specified that we want to stop when we hit, you know, our win amount. That's the missing piece of our condition in this loop. I only actually coded up the part where we lose everything and have to go home. But there's two conditions. I touched on this at the beginning. So if I want to indicate that in my loop, we have to join that together. I want to keep going while the start amount is greater than 0, and while the start amount is less than the win chance. So while both of those things are true, I'm going to stay at the casino and keep playing. If one of these things ends up being not true anymore, right? Ends up being 0 or less, or I end up hitting my win chance, then I will stop playing and I'll go home. So now if we try that, let's try and see if we can successfully simulate one day. Here's a start amount with a probability of 0.8, win limit of 200. Okay. What happened there? I think I coded something incorrectly because it jumped right down to... So I'm looking at this... That was the last piece of code that I changed, right? So let me think about this. I must have made a mistake, so let's figure it out. While the start amount is greater than 0 and the start amount is less... Oh, not the win chance. There's the problem. Not the win chance, the win limit. I'm sure some of you have been watching this video and noticed that a while ago. That's programming for you. There, that's more like what I expected to see. We can see the wins and losses. I've got some formatting issues with my text, but that's not a big deal. The wins and losses are now getting spit out, and you can see that with this game, I do properly hit my win limit, and then I go home. So I've sort of been ignoring the instructions for a little bit and just kind of hacking it on, but you know, I've been following along by using print statements to print out the number of simulations, and excuse me. I think that we do have a pretty good chunk of code here to simulate one day. Remember, this is just one day. I want to now continue this simulation by repeating this entire section. This is 1 day's worth. I might even put one comment here to indicate. Playing a game many times in 1 day. Right? Many times in 1 day. If we go back to that question that I asked before about whether a while loop or a for loop is the better choice, consider our condition. And do we know how many times we're going to have to play this game to either go bust or hit the win amount? We can make an educated guess, right? And probably be pretty close based on the numbers, but we don't actually know until we roll the dice and see the outcome of the games. That's the randomness involved. So while loops are really good loops to use when you don't know how many iterations it's going to take to complete whatever task it is. But let's take a look at the next step of this when we want to actually simulate this over and over and over again over a number of days. What I would like to do next is ask for another value, total simulations or total days, I might call it. I'm going to grab this scanner code one final time here. because of the randomness involved, we can't take one day's worth of games as representative of whether this strategy will work over time. So we really need to simulate our strategy over a long period of time to see if we're going to win or lose money. So let's grab an additional variable from the user to represent the total number of simulations, and I want to repeat this code, total simulations number of times. And because I know exactly how many times I want to iterate, even though it's in a variable, I don't know exactly what this number is. I don't know if it's 7 or 100 or 1,000. It could be any of those, right? But I know what the variable is. I think a for loop is a better task for the job here. So I'm going to use I as the typical for loop looped variable. I is going to be less than total simulations, right? Okay. I want to fix my indentation here real quick, just so that we can clearly see that we now have a loop within a loop. And the way that I intend for this to work is that this loop is going to run once for each day. So this represents going down to the casino for a day, and then this represents playing the games at the casino for a day. So let's try this out. I actually want to see, I may take these statements out, because really what I'm interested in now is whether I'm winning or losing for a given day. So maybe I'll update the statement down here to say something like day I is the day number that we're on, right? So if I is counting up from 0 up to the total number of simulations, then I is going to represent the day that we're on. Money, oops, I need quotes around that. There we go. And then I will tack the amount of money that I have on the end of this, so that at the end of each day I should be able to see how much money I've got, which should be either 0 or the win amount. Let's try it. So I'm going to start with, I'll stick with the easy game, right? The win limit will be $200, and the total number of days, let's simulate for 50 days. Okay. Wow. So you can see that for this one, it appears to be working, but let's see. Let's try. I mean, I do realize that it was a very strong, heavily game weighted in the player's favor, but let's try one that's maybe a bit more even, because I do want to see that it's properly tracking. I want to see both outcomes appear. I don't want to just see that I'm winning every day, right? The win let's do 50-50. I would then very much expect to win half the time and lose half the time. Okay. And so now I think you can clearly see we've got a problem here. This is telling me that I've won every single day. All right, so maybe I'll put these lines of code back in and see what the deal is, because clearly there's something happening. Something's not working. So let's see if we can see what the games are coming out as. 50 days. Okay, so this is interesting information. If you scroll up here to the top, you can see that it does look like the games are getting played. I see wins and losses showing up. Eventually, we do hit the win limit for day 0, which is fine. But then you can see that after that, it doesn't appear to be playing the games anymore. It's just giving us the win limit every single time. So let's think about what happened. This is actually a very, very, very common mistake. One of the most common questions that I get asked about on this studio is why the program behavior is only simulating one day when I'm trying to simulate many days. Think about what one day's worth of simulation represents. I wake up in the morning, I go down to the casino with $100. I either win until I get a bunch of money or I lose it all. Let's say I lose it all and go home, $0. The next day when I wake up and I go down to the casino, I start again with $100. I don't start with 0, right? I can't walk in with 0 even though I lost all that money yesterday, because I need money to play the games. So we're missing a step. At the very first part of our day, we need a way to reflect that we are restarting with a fresh amount of cash. So actually, I think we need a new variable. today's money is equal to the start amount. And then instead of updating the start amount, I'm going to update today's money everywhere, right? Including the conditions. I want this start amount value to stay constant because at the beginning of every day, I'm going to use this to reset where I'm at. So if I bust, today money is going to go to be either 0 or 200, right? And then at the beginning of the next day, I'll reset it to be the original value. This is a very, very, very crucial step, but a very easy one to overlook. So let's try this one more time. I'm going to use the 50-50 game again, the same values. So $100, win probability is 50-50, win limit's 200, 50 days. All right, now we can see it's churning out the wins and losses. So maybe I'll take these lines of code out because I don't actually want to see each individual game anymore. I'd rather see the amounts at the end of the day. So 0.5, win limit's 200, 50 days. There we go. So now we can see it does look like we've got a good mixture of days that I'm winning money, days that I'm going home losing money. I mean, it appears to be roughly 50-50 to me, which is what I would expect it to be given the parameters. All right, this is good. So we can actually compute then. There's a mathematical formula given down here that tells us what the expected ruin rate should be. So the amount of times that I bust and go home with no money. So we should actually be able to compute that, right? We should be able to determine based on the probability of the game and the other factors how many times we would expect to return home with no money. So what we want to do to kind of verify that our simulation is working properly is compute this value and then compare that against how many times we've actually verified the ruin rate, or that we go home with no money. So I'm going to insert a counter here at the outside of the for loop, rather. I'm going to call it num ruins. And so I'm going to set it to be 0 to begin with. We haven't simulated anything yet. No ruin days, so none to start with. But if I come down here and if I see that today money is equal to 0, I'm going to increment the number of ruin days that I've seen, like that. And then at the end of the program, after all of the simulations have finished, so I'm at the very, very bottom of the for loop now. So after all the simulations have finished, I'm going to print out the number of simulated ruin days and then I'll print out the number of estimated ruin days, or the computed number of ruin days, rather, using the formula that's been given. So let's compute that formula. It's based on the parameters. We can see there's actually two cases here. If the win chance is 0.5, then we use one formula. If it's not 0.5, then we have to compute an additional term called alpha. So let's go ahead and start that out. So if the win chance is equal to 0.5, notice that I'm using double equals here. Double equals is how we test to see if two values are equal to each other. Single equals is used for variable assignment. So if the win chance is 0.5, then let me make a variable. Will this be an integer? What's the data type? I chose double. Start amount, win limit. I'm going to choose a double. But yeah, we'll see. All right, so set it to be 0, but then we're going to look at the win chance and compute it based on the given formula. If the win chance is 0.5, it is 1 minus the start amount over the win limit. Okay, so minus start amount over win limit. These are both integers, I believe, so I'm going to cast one of these to be a double. Make sure that that gets computed properly. I'm not doing integer division there. Otherwise, I now have to compute this alpha term. The alpha term is given to us as 1 minus the win chance over the win chance. Okay. Minus win. I'm sorry, what did that say again? 1 minus. Oh, okay, gotcha. I do need to use parentheses. I just didn't put them in there properly. Here we go. And after we have computed alpha, we can now insert it into this expression here. It's asking us to do powers. So this is going to be another time to use the math library, math.pow. So we need to take alpha to the start amount, alpha to the win limit. I'm sorry, I'm just going to do expected ruin is equal to math.pow alpha to start amount minus math.pow alpha to the win limit. And then all of that is going to be the numerator. And then in the denominator, we have 1 minus alpha to the win limit. So divided by 1 minus. I could have, and perhaps arguably should have, used some variables to clean this up a little bit and make it a little easier to see. This line of code is quite long as written. So probably a bit too long for my liking, but I do believe it'll work. Let's go ahead and make sure we add these variables onto our print statements and take a look at the results here. So I'll run two examples, one with 50-50 and one without, so that we can check both. Here we go. For 50-50 probability with a win limit of 200 over 50 days, you can see that, whoops, okay, definitely appears to be something computed. Oh, or I'm computing the ruin rate. The ruin rate is the percentage, not the total number. So I need to actually divide this by the total number of simulations before performing that comparison. And as before, I probably need to cast one of these to a double so that that does not lead to some integer division. There we go. This looks much better. The simulated number of ruin days was 0.44, so not exactly 50-50, which is what you would expect, right? There is some randomness involved. I mean, it should be hovering around 50-50, but I wouldn't expect it to be exact. The number of ruin days that it expected is in fact 50-50, although if I change the win limit, I think I would expect that to change. So if I use the same probability and increment the win limit to be, like 500, then I think you can see, okay, good. The number of, the ruin rate went to be 80%, and you can see that it was in fact around 80% ruin rate, since the amount that I was trying to win went up so significantly, right? Let's try one without 50-50. So I'll do 100. I'll do a pretty, I'll do like 40% with the win limit of $250 and 50 days of simulation. You can see, oh wow, expected me to lose every single day. Really that bad of a game, huh? Not favorable conditions at all for the player. So let's try and see if we can find something a bit more interesting, perhaps. The win limit of $150 might do the trick. Okay, so this did expect me to win, at least some of the time. Wow, this is, I think, a good illustration of how bad casino gambling is. Yeah, even for a $120 win limit with 40%, right? You're still expected to lose 99.9% of the time. Truly, casino games are not in your favor. Let's see, 48%, right? Does move the needle a little bit. You can see that we actually do expect to win sometimes. So yeah, as soon as the probability tips one direction or the other, it really has a significant effect on how well you can expect to do on these casino games. I'm not sure if I hit every single piece of the studio, but I think I hit most of it. So I'm going to move on to the second problem. I know that many people didn't get a chance to get to this problem. This is one of my favorite problems, though, of all time, like of any problem that I've ever worked on in computing. So I do want to go over this one real quick. I think to do that, though, it's important to understand the setup first. So I'm going to start by drawing a very bad diagram in Paint to illustrate what we're working on. We have a unit square dartboard. Pretend that that's actually, an equal square. It's pretty close. I can see how close it is on the bottom there. It's pretty close to being a square. We're going to assume that it is. And then within that, we have a circle. So can I draw a nice... Oh, that's not the way to do it. Not at all. I need to start from the corner. Here we go. So within that, we have a circle. And we're going to assume that for the sake of math, it definitely makes it simpler to keep, this as being the coordinate 0, 0 down here in the bottom left, and then up here in the top right, you could consider this to be 1, 1. And we're now going to assume that we have a bunch of darts, an infinite number of darts perhaps, and we're going to start throwing them, and we're guaranteed that each dart is going to land inside of this square somewhere. So let me get a bigger pen tip. How do I... Oh, yeah. So we're going to imagine that each of these darts lands in the square somewhere, right? Okay. And so what I want you to notice is that some of the darts are going to land in the circle, and some of them will not. Some of them will land outside of the circle. And if we do this enough, the idea is that we can use the number of darts to approximate the areas of the respective shapes. So if I throw enough darts, right, I can use the number of darts that land inside the square to, represent the area of the square, and then I can use the number of darts that land inside of the circle to represent the area of the circle. From geometry, we know that the area of the circle is going to be pi r squared. Ooh, look at my handwriting in Paint. That's really bad. And then from the area of the square, since the radius, right? So 2 times the radius gets us one side, and then we're going to square it. So that gets us 4r squared for the area of the square. The r squared terms cancel out, and what we're left with is a factor of pi over 4 that represents the ratio between the area of the circle and the area of the square. And since we're using the darts that are thrown to represent the areas of the circle and the areas of the square, we can then use this to compute pi, or more specifically pi over 4, and then get pi. The trick is that we have to throw a lot of darts for this to work. If we only throw 2 darts, we don't have enough information. This only works if we throw a lot of darts. So we're going to write a simulation for this that simulates throwing a lot of darts so that we don't have to actually do this ourselves. That would take a very long time. We're going to use a computer to help us out. We have a name for this. This is called Monte Carlo simulation. Anytime we are simulating a large number of random events, in this case the random events are going to be the dart throws, it's called a Monte Carlo simulation. It's a common simulation type used within computer science. So let's make a new file for us to work in. I'm going to call this one pi. Oops, I forgot to put in the main method. That's okay, I'll just type it out myself. Okay, the first thing that we need to do is pull in the scanner because we need to ask how many darts we're going to throw. Oops. And we'll import. I'll print out a message. How many darts? And then we'll use the scanner to pull in an integer number. Okay, I now want to simulate that many number of dart throws. So that requires some repetition, and I know how many times I need to repeat. Once for each number of darts. For int I equals 0, I is less than the number of darts, I plus plus. You might think that it's a little strange that I'm starting from 0 here and using strictly less than, but it does work out, and there is a reason that we do this. It's a very common way to write loops. You'll see a more clear reason why next week when we talk about arrays. But for now, consider that to throw a dart, I need to figure out where it lands on the dartboard, right? So position requires two pieces of information, an x coordinate and a y coordinate. And because we carefully chose our coordinates here, right? An x coordinate's going to go from 0 to 1, and a y coordinate's going to go from 0 to 1. So I can randomly choose two numbers from 0 to 1 to represent x and y. Okay. Double x is equal to math.random. Double y is equal to math.random. There we go. This is going to represent our dart throw. And we now just have the task of figuring out whether or not it is landed inside of the circle. Remember, we know that all of the darts are going to land inside of the square, but we do need to determine whether it's landed inside of the circle or not. So we need to figure out if the distance from the center is less than the radius of the circle. So let's go ahead and pull up our good friend distance formula. Everybody Googles the distance formula when they need it. Don't kid yourself otherwise. Distance formula. All right. Double distance equals. We're going to go to the math library again to pull out math.square root. And this time we're taking the square root. Oh, so we have to use math.pow as well. And that's fine. So math.pow of, we're going to use x minus 0.5 squared, right? That's the first term. We're comparing our generated value against 0.5 plus the y value minus 0.5 squared. So we'll copy this term plus copy that term and switch this to be a y. And that should get us our distance. If the distance is less than 0.5, I know it's within the circle, and I want to keep track of that. So I'm going to come up here and make another variable. And then if I determine that it's within the circle, I'll add 1 to indicate that that is taking place. Once I have simulated all of the dart throws, I now just have to do some division and multiplication. Double pi over 4 is going to be equal to let me refer back to my diagram. Yeah, the number within the circle over the total number, right? So num circle over num darts, you'll again notice that these are both integers. So as before, I'm going to cast one of these to a double to make sure that I don't run into integer division. And then I'll just print out pi over 4 times 4, and that'll be our computed value of pi. Let's try it out. So I mentioned that if I use a small number of darts, I get bad values, right? So if I put in 10, I get 3.6. I mean, we're, you know, kind of in the ballpark, but that's not pi. If I use 100, right, I get, okay, 3, closer than 3.6, yes, but still not great. Let's try 1,000. All right. 10,000. Oh, now we're getting closer. This is the fun part, right? 100,000, 3.14, but then that's not right. 1,000,000, 3.14, still not right, but getting closer. 10 million, 3.141. You can see it is getting closer and closer. 100 million. 3.1416, so close. Can I do, that was what, 100 million? So the next one would be 1 billion. 1 billion. Boom. Now this one, you know, is going to take a noticeable amount of time. The last one took a noticeable amount of time, and as I've been using larger and larger numbers, you'll probably realize that yes, I do have to simulate more and more dart throws, which, while the computer is very fast, it does take time to do that. So as I use larger and larger numbers, we do see that things start to slow down. This will eventually complete, I believe, but you could consider that if I keep typing in larger numbers, that I'm going to eventually get to a point where I may not be guaranteed for it to complete, at least not in a reasonable amount of time, or today, or even in my lifetime. It's possible to conceive of programs that run many human lifetimes. Oh, hey, there it is, 3.1416. You'll see that it's still botched, you know, after the first few digits there, right? So still not perfect. Still have to use a lot of darts, but does get you a very close approximation to pi. Definitely not the way you would normally want to, you know, use pi, but a fun simulation nonetheless. Okay, that's going to wrap it up for today's studio review. I hope this was useful for you. You are now tasked with working on the next homework assignment. So this homework assignment I do think is going to be a bit trickier than the last one. There's a lot of things that we're asking you to think about for this one. So just pay attention to all the different cases and conditions that can happen, especially towards the end of this game. It's a very simple sounding game. You only have to pick up a couple of sticks or tokens every round, but it does have a surprising number of different ways that you can kind of wiggle through. And we're also going to address a problem that we dealt with last time, which is that we don't want to allow bad input. So on the last homework assignment, we didn't really ask you to worry about the case if somebody typed in a negative value for an average, or attended, you know, 100 studios in a semester. You know, how would that affect the grade? But we do have enough knowledge to deal with that now. So now, as we use scanner to prompt for inputs, we need to look at the input that's been typed in, and if it's bad, we need to ask them to give us another one. So think about what construct you would use to pull that off, and consider the very important fact that just because they get it wrong the first time and you ask them to enter it in, doesn't mean that they're going to get it right the second time either, or the third time. They may give you many bad values in a row before they eventually enter a correct one. Actually, they may never give you a correct value, right? That's possible too. Okay, that's all for now. Get to it, and as always, please let us know how we can help you. Have a great weekend, everybody.